Hi and welcome to video 4 on my series on definite integration, and in this video we're going to explore one last example of finding enclosed areas of situations where you have negative and positive components. So we've got here three areas that distinctly stand out: area 1, area 3 and area 2, which is above. What's going to happen here is when I do my final calculation, I'm going to recognize that two of those areas are negative and I'm going to make them positive. And there's multiple ways that we can do this. But first, the example actually asks us to do two things. One, evaluate that, and two, find the enclosed area. So the first thing I'm going to do, which I'll call part A, is evaluate that integral. 4 to negative 1 of 3x minus x squared dx. Well, that's equal to 3x squared over 2 minus x cubed over 3 between 4 and negative 1, and that's equal to 3 times 4 squared over 2 minus 4 cubed over 3 minus negative 1 squared, 3 times that, over 2 minus negative 1 cubed over 3. And we can't overdo the brackets here, so we're subtracting all of the negative 1 component here, so we have to make sure we've got brackets around that. It's easy if I put brackets around this as well. So we've basically got the 4 substitute and the negative 1 substitute, and we've got a negative in between, so just be really careful with that. So our answer in this case is 5/6 unit squares, and of course we can use our calculator to determine the accuracy of that answer as well. So here's our calculator. If we go into the run matrix screen and we go math, we click F6 to go across and we do an integral. Of course we're going to do the integral of 3x minus x squared, and we're going to do that integral between negative 1 and 4. Execute, and that gives us 5/6. So we know we've got the right answer. But that of course is the definite integral. So now that we've got the definite integral, we need to recognize that some elements of this definite integral were counted as negative areas. So actually we need to calculate the positive area, which I'll do over the side here. Now we could use the fact that A1 and A3 are symmetrical, and I'd encourage you to consider that because a quadratic is symmetrical. Periodic function has nice symmetry as well, but I'm going to instead just do each three of the three parts separately and show they're symmetrical. So A1, we can see our intercepts here at 0 and our boundary at negative 1. A1 is going to be the integral between 0 and negative 1 of 3x minus x squared dx. And this will be, I'll do it running down, 3x squared over 2 minus x cubed over 3 between 0 and negative 1. And again, we can substitute those values and then do the calculations on a calculator. So it becomes 3 times 0 squared over 2 minus 0 cubed over 3, brackets around that, and we subtract from that 3 times negative 1 squared over 2 minus negative 1 cubed over 3. So I'm really careful to make sure I've got the right amount of brackets to cover everything, including around the negative 1 and even the 0. Now this turns out to equal 0. When we evaluate this final answer, we get 1 and 5/6 units squared. But of course there's a negative in front there, so it's negative 1 and 5/6 units squared, which is what we expected. For for area 2, we get the integral between 3 and 0 of 3x minus x squared dx. And we're going to start to see some repeats here. So we get 3x squared over 2 minus x cubed over 3. That's the obvious repeat. But the 3 and 0 give us a repeat on the 0. So when we substitute this in, whilst we get 3 times 3 squared over 2 minus 3 cubed over 3, we get the same thing over here. 3 times 0 squared over 2 minus 0 cubed over 3. So in this case that's 0, as we calculated earlier, but sometimes it won't be 0, so don't be afraid to go back and look at the same boundary you've already calculated once. And we calculate out 3 times 3 squared over 2 minus 3 cubed over 3, and we get 4.5, or 9 over 2 units squared for that calculation. Finally, we need to calculate our A3 value. And A3, I'm going to show you between 4 and 3 is actually the same as we had earlier. So we have that symmetry. So we're doing 3x minus x squared dx. This gives us 3x squared over 2 minus x cubed over 3 between 4 and 3. And that gives us 3 times 4 squared over 2 minus 4 cubed over 3. That's the 4 substitution. Minus 3 times 3 squared over 2 minus 3 cubed over 3. And this gives us the 4 substitute from earlier. And we've done the 3 substitute earlier as well. So again, don't be afraid to use those values. And that's 2 2/3 minus 4 1/2, which actually gives us negative 1 5/6, as we expected from our earlier calculation of A1. But it's always good to verify that sometimes. This means that the area total is equal to the sum of those, but we have to negate the positive areas. So we can use an absolute value sign to do this. 1 5/6 plus 4 1/2. Let's do 9. Oh no, let's do mixed numbers. 4 1/2, and then plus negative 1 5/6, and that's equal to 8 1/6 units squared. So there we have it, a calculation of the area of a 3-part problem where you have some negative and positive areas, but also another reminder about the difference between definite integration and integration to find an area. In the definite integration, you can get a negative or positive answer, and negative areas just continue to count as negatives because we're not worried about the area, whereas the area calculations, we have to make sure that they're positives. Always sketch the graph or use your graphics calculator to evaluate a required area, as I've made a note down here. It's really important to be considerate of what might be happening in the background. If it's a tech-free paper, then just be aware of and know your functions, such as this quadratic here. All the best.